In this video, I'll be going over z-scores. The objectives are students will be able to develop the ability to compute a z-score and use the result to determine whether a given x value is significantly high or significantly low. This video goes along with pages 1 and 2 of the 3.3 Measures of Relative Standing in Boxplots notes. Please have your notes out so you can follow along. A z-score is a way of standardizing data. A z-score is also called a standardized value. What it represents is the number of standard deviations that a given x value is above or below the mean, rounded to 2 decimal places. As a note, the z-score has no unit of measurement attached to it. What it tells you is how many standard deviations above or below the mean a data value is. So what that means is if a data value falls below the mean, it should have a negative z-score. If a data value falls above the mean, it should have a positive z-score. And if a data value is the same as the mean, the z-score will be 0. Here we have formulas for z-score. It's the same process with a sample or a population, but remember we use different notation for samples and population. So z equals x, your data value, minus the mean, divided by the standard deviation. We can manipulate that formula. Z equals x minus x bar over s in order to solve for our x value, because in some problems we'll have x and in some problems we'll have z, and we want to be able to go from one to the other. So what I can do here is I can multiply both sides of my equation by s, and I'll have s times z equals x minus x bar. And then I can add x bar to each side. And I'll have x bar plus s times z equals x. So I can write that as x equals x bar plus sz. In population format, that would be x equals mu plus sigma times z. It's important to have both forms of the formula so we can translate from x to a z-score, or we can translate from a z-score to an x value. For these examples, we are going to take each given x value and convert it into a z-score. I have the formulas written right here as a reminder for us. For the first one, we have x is 4.2. And we're subtracting the mean of 5.2. And we're dividing by our standard deviation of 1.3. And we'll get 4.2 minus 5.2 is negative 1 over 1.3. Gives us negative 0.77 when we round to 2 decimal places. So the number 4.2 centimeters is 0.77 standard deviations below the mean. Next, example B, we have x is 7.1 and we'll subtract the mean of 3.6 pounds. And the standard deviation is 0.8 pounds. Here we get 3.5 over 0.8, giving us a standard deviation of 4.38 when you round to 2 decimal places. The next two examples have to do with population data, but the process is the same. We'll take our data value of 112 feet and subtract our mean of 112 feet and divide by our standard deviation of 13.8. Well, we'll just have 0 over 13.8. So the z-score, z, equals 0. And that makes sense because the data point is right at the mean. So it is 0 standard deviations above or below the mean. And lastly, we'll have our x value is 1.57 centimeters, and we'll subtract our mean of 1.57 centimeters. And we'll divide by our standard deviation of 0.32. This is another example where we'll get 0. For example 2, we're asked to convert the z-score into an x value. If we know that z is negative 2.38, x bar is 68 beats per second, and the standard deviation is 3.8 beats per second. Remember, we solved to find that x is equal to x bar plus S times Z. And we can just fill in what we know. The mean X bar is 68, S is 3.8, and the Z-score is negative 2.38. So go ahead and calculate. We get 58.956. And since it's the X value, it'll have the units of beats per second. In question 3, we're asked to find a different variable. We're asked to find the mean. A data set has a standard deviation of 1.1. There's a piece of data, x equals 7, and the z-score corresponding to it is negative 0.55. Given this information, we want to find the mean. So we'll take our z-score formula, z equals x minus x bar over s, and we'll fill in what we know and solve for what we don't know. So we have negative 0.55 for z equals 7 minus x bar over 1.1. And I want to solve for x bar. So what I'm going to do is I'm going to take both sides of my equation and multiply them by 1.1 to get rid of the 1.1 that I see in the denominator. So those will divide out. On the left we have negative 0.605, and on the right we have 7 minus x bar. I want to get x bar by itself, and right now it's being subtracted from 7. What I can do as a first step is I can subtract 7 from each side. So I'll have negative 7.605 on my left and negative x bar on the right. X bar is negative and I want it to be positive, so what I'm going to do is I'm going to multiply both sides of my equation by negative 1. And I'll come up with my answer of x bar equals 7.605. Now we've learned the values that are more than 2 standard deviations from the mean are considered significantly high and significantly low. Well, if you're a value that is more than 2 standard deviations from the mean, that means that your z-score is greater than 2 or less than negative 2. So we can say that unusual values or significant values have z-scores of less than or equal to negative 2 or greater than or equal to 2. We'll call them significantly low or high. Let's look at some examples. It says, in which of the following 2 data values is more extreme relative to the data set which it came from? So z-score is because it will standardize the data. It will allow us to compare 2 different things that we otherwise couldn't compare. We have a 4,000 gram weight of a newborn baby among 400 weights with a sample mean of 3,152 grams and a sample standard deviation of 693.4 grams as our first example. So we can say that x is 4,000. We know that the sample mean, x bar, is 3,152. And we know the standard deviation, s, is 693.4. We can now fill in our z-score formula. 4,000 minus 3,152 over 693.4. We get a z-score of 1.22, meaning the baby with a weight of 4,000 grams has a weight that is 1.22 standard deviations above the mean baby weight for the sample. The next part of the example says that a 99-degree temperature of an adult among 106 adults with sample mean of 98.2 and a sample standard deviation, S, of 0.62. We want to determine the z-score associated with that. So we'll have z equals 99 minus 98.2 over 0.62. The z-score is 1.29 in this case. So that means that the temperature of 99 degrees is more extreme relative to its data set. Why? Because the value is more standard deviations away from the mean of its data set, because 1.29 is greater than 1.22. For our final example, we have the lowest platelet count in a data set is 75. Is this value considered significantly low? We want to assume that platelet counts have a mean of 239.4 and a standard deviation of 64.2. And the x value you're comparing is 75. So we know that it would be significantly low if it was more than 2 standard deviations below the mean. Let's find the z-score. We can take our value of 75 and subtract our mean, 239.4, and divide by the standard deviation of 64.2. We get negative 2.56 for the z-score. Well, negative 2.56 is certainly less than 2. So yes, we would consider this significantly low. Because it is more than 2 standard deviations below the mean. We know it's below because it's negative.